Welcome to online lecture number 17. The last time we spoke about the negative mesomeric effect, and here is an example where a negative mesomeric effect stabilizes a negative charge on this oxygen. This carbonyl oxygen here is stabilizing this system because the pi bond here can jump from one position to the other. It is delocalized at any time. It is not at one position between the carbon and the oxygen, but it is somewhere at both positions at the same time. This is called delocalization, and the delocalization can be described in terms of the energy reduction of the orbitals, where you form this pi network or a pi scaffold, which has a lower energy than the constituents orbitals that it was formed of. And the reason why the energy is lowered is due to the delocalization of the electron density. So in the carboxylic acid here, the electron density is now distributed over all three atoms, the two oxygens and the carbon. In the 2 pi orbital, there is less delocalization, but still you have delocalization over the nth oxygens. So generally speaking, the negative mesomeric effect, it occurs in functional groups that are electron acceptors and that have a pi bond, right? So the important aspect about the pi bond is this delocalization principle. And here are examples of electron acceptors of negative mesomeric groups. So you see the oxygens, the carbonyl oxygens here, they are willing to accept electrons, for instance, from the pi bond that is formed here. And when this happens, another pi bond will form at a different site, and this is this delocalization. So it can happen with carbonyls, it can happen also with double bonds between carbons. They can also act as electron acceptors, the carbons, and of course the highly delocalized benzene system as well. So important is electron acceptor and pi bonds. So there's also a positive mesomeric effect. Just how there is like a negative inductive and a positive inductive, there is a negative mesomeric and a positive mesomeric. So the positive mesomeric effect, it's also based on delocalization of pi bonds, but now in conjunction with an electron donor that has a lone pair. Now here are examples. You see the chlorine, for instance, it has only one bond to the residual scaffold, but it has a lone electron pair, as the bromine as well, or here the amine from this nitrogen. So these can donate electrons. So it is a filled p orbital that you have here, and it can give an electron into a pi system that can form with these additional groups here. So this is a positive mesomeric group. Here are more examples. Also oxygen can act as a electron donor to from its lone pair in the hydroxyl group here to the residual scaffold of the molecule. And surprisingly, even the double bond between the two carbons, we saw before, it can be a negative mesomeric group, but it can also be a positive mesomeric group. So electron density from this pi bond can move to somewhere else, causing a positive mesomeric effect. So we've seen before, minus M groups can stabilize carb anions, but plus M groups, they stabilize carbocations. So this is the allyl cation. Before we spoke about with the minus M group, we spoke about the allyl anion. Now this is the allyl cation. So here there's not an electron in excess, but there's an electron missing. So the carbon here at the end, it has an empty p orbital here that has no electrons in it. Additionally, there are two hydrogens here that are not drawn, and there's one bond to the adjacent carbon. So this is an sp2 hybridized carbon with an empty p orbital. But because of this positive mesomeric group, this double bond here, what can happen is that the electron from the double bond, from the pi bond, is now donated to form a additional into this empty p orbital of the carbon, and that results then in the formation of a new pi bond between these two carbons. But the other pi bond has been lost, and therefore the positive charge, so the missing electron, that is now located here, because the electron had jumped from there to over here, and that causes the other end now to be positively charged, right? So, and of course this process, it can also go the other way around, and therefore this arrow here is a double-headed arrow to highlight that this is a resonance state where you have a resonance hybrid. So at any given time you never have really either this type or this type of the molecule. Both of them are present simultaneously in this resonance hybrid. So the curly arrow notation here is just drawn to kind of explain how the electron distribution takes place on this molecule due to the positive mesomeric effect. So it's just the same principle as you've seen for the negative mesomeric effect. It is stabilization based on delocalization that eventually it leads to lowering of the energy. So here's a more complex system with a vinyl ring, and now we have an empty p orbital at this side methyl group. So this has a lack of electrons, and again the double bonds here, they can donate an electron to form a resonance form where the double bond now is located over there where there previously was a positive charge, and since the electron is now missing in between these two carbons, the positive charge is now located over there. But now this can continue. The group here at this side that's positively charged can get an electron donated from this adjacent pi bond, and then you have the positive charge at the bottom, and now this adjacent pi bond can again donate an electron, so the positive charge will be located there. So, and these are all the different resonance forms. You can see these two are basically equivalent. No? I mean, you just need to rotate them and then they are the same. So they are two identical resonance forms. And therefore, this is the most stable resonance form because of the identity between these two. And all the four different resonance forms together, again, they make a resonance hybrid, a positively charged a carbocation. But since this is the most stable group, the partial charge in this resonance hybrid is drawn to be the strongest here, the partial positive charge, while the others have a lower partial positive charge. So now, this was now electron donation by pi bonds, but here is an example where there's electron donation from a from a lone pair. So the carbocation again has an empty p orbital over here, and the oxygen that is adjacent, that has a lone pair, right? So the oxygen makes two bonds here to the side, and it has additionally a lone pair. And now this lone pair can donate electrons to form a new double bond here, and that double bond now is basically between the p orbital and the oxygen, and therefore the oxygen now becomes positively charged. So again, stabilization by delocalization. So now we are at the end of mesomeric effects, but also at the end of electronic effects in general, electronic effects that stabilize reactive intermediates. There were three different types of electronic effects. There were inductive electronic effects, there were hyperconjugation electronic effects, and there were mesomeric electronic effects. All of them can stabilize either carboanions, carbocations, or radicals, and which type they stabilize depends on whether they are positive or negative effects. But all of them are classified as electronic effects. And the second big approach to stabilize reactive intermediates are so-called steric effects. So they are much more easy to understand, And that's why we actually only spent this one slide on them. So steric effects, for instance, you can find them in this reactive intermediate. That is a radical carbon here with an unpaired electron. And there are these 3 vinyl groups. So you have to imagine these are very bulky groups. They occupy a lot of volume around the carbon, and therefore they shield the carbon just based on their on the volume that they occupy from nucleophiles or from other radicals that want to react with the carbon. And this is called steric hindrance. So steric stands for this shielding effect that's just based on that there's material blocking access to it, right? So, but here this is special because of the mesomeric nature of the vinyl groups. There's not only steric stabilization, but also there's a delocalization now involved that leads to additional stability. So this is a very, very stable reactive intermediate that was actually discovered at the beginning of the 20th century. So steric acceleration is another concept. So here is this bromocarbon that has these 3 methyl groups. At the moment that's an sp3 hybridized system. And when the bromine breaks off, you transition to a planar geometry of the molecule and you obtain a carbocation. So now you can imagine this one here, sterically it has more surrounding this central carbon. No? So this is sterically more stable, but now the carbon here is less protected by its surroundings. So it's a weaker steric effect for this as compared to that one. Okay, so there we are at the end of the stabilization of reactive intermediates via electronic or steric effects. So with the knowledge from this series of online lectures now, you should be able to tackle the homework problems 19.1, 19.3 and 19.4. Good luck and see you next time. Bye.